So we've looked at taking derivatives of pretty much every type of function except exponential functions. And so a reminder is an exponential function is just a function where x is in the exponent. So we might have y equals 2 to the power of x, and this is the definition of an exponential function. We also can see that in a more complicated way. So maybe it's not just x, but maybe x is actually a polynomial in some case. So in order to understand this, we're going to go back to our initial understanding of derivatives, where we're looking at the change in the function value over a small change. As h approaches 0, how does the difference in the f at x change? So the limit as h approaches 0, now we're going to have an exponential function. So we have b to the x plus h minus just b to the x all over h. So what I can see here is I actually have, I'm going to use exponent law to say that b to the x plus h is actually b to the x and b to the h. And now that I've done that, I can see I actually have a common factor here. So I can actually take b to the x right out, and then I just have b to the h minus 1 over h. Now, if you remember way back from the beginning, the limit of a constant is just a constant. So I can bring this out front, and I can get this definition that the derivative is actually the b to the x, the limit as h approaches 0, of just b to the h minus 1 over h. And now at this point, we can't really do anything else because we don't know what to do with this. And what ended up happening was this guy named Euler figured out that there was a really special number for a derivative. He found this number for b such that the derivative was exactly itself. So this is Euler's number. It's e, and so he found a perfect exponential function so that the derivative of this function is actually itself. So this graph here, this blue line is, this red line, sorry, is y equals 2 to the x, and this line is y equals 3 to the x. And then we have this really special function here, kind of in the middle, and this is y e to the x. And this value e is somewhere in the middle between 2 and 3. It's about 2.7, et cetera, et cetera. And all that to say is that we really can just now use that because now we have an exponential function that is the derivative of itself. So the slope of the tangent is the same as the y-coordinate of the original function. So the function and the derivative of the function are exactly the same. And so now we can write this statement. So if f of x equals g to the x, or equals e to the power of g to the x, then the derivative of that is just e to g to the x, because that's what the constant that we knew before, and now just the derivative of the exponential value. Okay, so as long as the base is e, then now we can take the derivative. So let's try a couple examples. So we're going to take the derivative of the following. So the derivative of e is itself, it's e. So I have to write this again, 3 to the x squared. And then I have to take the derivative of whatever g to the x is, which is 3 to the x squared. So in this case, I'll have 3 times 2 times x minus 2, which is 1. Now I'm just going to rewrite this so that it looks more organized. I'm going to put the 6x out front and then e to the 3x squared afterwards. Let's try it out. In this one, I've got the chain rule here. So I'm going to have the derivative of the first, which is 4x3, and I'm going to just keep the second. Now I'm going to add a keep of the first and a derivative of the second. So the derivative of e to the x is e to the x, and then the derivative of x, which is just 1. Now I'm going to reorganize this just so that it looks... And I'm going to notice that I actually have some common factors here. So I'm going to pull out x to the power of 3, e to the x, and 4 plus x, and there's the derivative. All right, well, what if we have a sine function? All right, well, I have a constant, so that just stays. And I have e as my base, so that also just stays. And now I'm going to take the derivative of the exponent, which is sine x. So the derivative of sine x is cos x. And just rearrange. Okay, final one. Let's try a quotient rule. All right. First step, take the derivative of the top, 2x. Keep the bottom. Now subtract. Keep the top. Take the derivative of the bottom. So the derivative of e to the exponent 2x is 2x times the derivative of the exponent, which is 2. All of this is over e to the 2x plus 1 squared. I'm just going to reorganize this a little bit. I'm going to keep it and we have a 2 x squared minus 1 e to the 2x. I'm going to look for any common factors just so I can simplify further. All I see here is this 2 right now. I'm good with the 2 out front. All over e to the 2x plus 1 all squared. Okay, that's it for that. All right, let's try this word problem. So determine the equation of the tangent to the curve defined by e to the x, sorry, this is a typo here, should be y equals x e to the exponent x at the point 1 e to the negative 1. All right, so first up, I need to take the derivative. So my function is y equals x e to the negative x. Chain rule here, so derivative of the first, keep the second, plus keep the first, derivative of the second. Clean that up. Factor. Okay, and so here is my derivative. And now I want to know when the derivative is at 1, what's the value? So I'm going to put in negative 1 for x. And that's going to equal 0. And so now I'm going to write the equation of the line. I'm going to use y equals mx plus b. Actually, let's use point form. Y minus the y value, which was e to the negative 1. So the point that I'm looking at is 1 e to the negative 1 equals my slope, which I just found is 0, x minus 1. So the equation of the line is y e to the negative 1. Okay, for homework, page 367, numbers 4 through 9.